In this video, we're going to get deeper into this concept of what a critical point is, and what a minima maxima are. Now, we're going to leave for our next video what the saddle point is. But in a sense, I already placed here on the left side of the screen the same the graph that we got in the previous video, which is the graph of x squared and then the graph of its derivative. F prime of x will be 2 times x. And here is the connection between these two graphs. This f prime of x equal to 2 times x represents the slope of all the tangent lines that you might have or sketch. You might have for the f of x equal to x squared, just like the ones I sketch up here on the graph. And as you can see, the tangent lines are positive, and so you can connect it with the f prime of x, where after the 0, all in this case would be positive. All the values for the derivative will be positive, and that's why we have the positive tangent lines. The increasing tangent lines with a positive slope. And so you can infer with a negative and a decreasing tangent lines that have a negative slope, this ugly negative. And you can see how on this on the graph below, all the graphs that are before 0 are below the x-axis. Well, there is this point where the f prime of x has the value of 0, which has a horizontal slope, a horizontal tangent line with a slope equal to 0. So, in a sense, then we got to this idea of what a critical point is. We got there. That's where when you equalize the derivative to 0, you get a critical point, and there are 3 types of critical points. The maxima, the minima. I think you can really, it's pretty clear. You can say, well, this might. You have to pick out of the 3 options, which would be this the one you have, the critical point when the derivative is equal to 0. Well, I think in this case, pretty safe to assume that you can. Well, this surely should be a minima. But now let's look at this new example that I already prepared for you. In this case, on the right side of the screen, we got the f of x equal to x to the third minus 3 times x would be the function. And already, look, here's the graph, of course, of this f of x. And I already placed here the derivative of this guy, which is the derivative, the f prime of x would be the derivative of this previous f of x, is 3 times x squared minus 3. And I already located here the graph in this case, which is slightly more complicated than the one in the previous example. This one is a quadratic function for its derivative. But let's work through it and find the critical points following up this criteria for this second example. So I'm going to start, of course, the derivative of this. I'm going to do all the steps. If we have the x squared, the f of x equal to be x to the third minus 3 times x. We get the derivative out of it pretty nice and easy. It will be 3 times x squared minus 3. And then in order to find the critical points, we have to equalize to 0 the derivative. 0 equal to 3 times x squared minus 3. And then we got to solve for this, to find the critical points. We got to solve for this expression. Now, there are 2 ways we can do it. I'm going to do it, through factoring, why not? So I'm going to get a common factor of 3 first, common factor of 3, and then we got inside would be x squared minus 1, and then we can factorize the x squared minus 1, of course. Be here x minus 1 times x plus 1, there it is. And we get 2, of course we are equalizing this to 0. This 3 has no x factor, so it is not properly a critical point candidate. But from here we got 2 possible critical points would be x equal to, we solve here for, would be x minus 1 equal to 0, of course. I'm going to make it on the left. X minus 1 equal to 0. And this will be producing a critical point in x equal to 1. Well, we can do, of course, the same with the other guy. It will be x plus 1 equal to 0. We solve for x, and will be x equal to negative 1. So at the end, we got 2 critical points, x equal to 1 and x equal to negative 1. Now, what represents this on the graphs? Well, okay. Looking at the graphs, well, we got this x equal to negative 1. Of course, here we got here on the of x equal to -1. And we can pretty much see on through the graph that before the -1, if we sketch any number of tangent lines here, we have here positive tangent lines, positive tangent, they're increasing, and then we got this point at the peak, at the top of this hill, let's say, where the derivative is equal to 0 because here it stops increasing, all the tangent lines stop increasing here, and we got a horizontal where we got here with the the slope being equal to 0 at the top, and then the derivatives will be decreasing and then decreasing the slopes. I mean, here would be down here, and then on x equal to 1, which is the other critical point, this guy. So at x equal to 1, we got again at this bottom of this valley, let's say, we got this horizontal tangent line where its slope will be equal to 0, and then we'll start again growing up. I mean, the positive tangent lines, positive slopes, increasing tangent lines. I guess it could be drawn better, but that's it. Well, as you can see, we got on the first side positive slopes. We're going to say here m greater than 0, then we stop and get an m equal to 0. And all this area, this period in between, we got negative slopes, and then we got again the equal to 0, and then we got again positive slopes. And I think you can pretty much, now let's compare this with the graph of its derivative. As you can see, before the -1, all these values are positive, are above the x-axis, and that is why you got here the slopes. I mean, the m will be positive, greater than 0, and then once you reach the -1, up here on the -1, then you have negative values. You have below the x-axis, and that's why you got the negative, I mean, the m lesser than 0. I mean, the negative values on here. And then you reach to the positive one up here, and then you again start increasing on the previous graph in the f of x, and that's why you got, I'm going to actually write here negative sign. Here is a negative sign, and then you got again positive values above the x-axis, positive values. There it is. Now this would be pretty much the idea, but let's do something else. There's, of course, we figure out the behavior of this graph because we already have here the graph actually. So let's see, start using the names that we learned on the previous video, and then let's present a proof for these ideas, how to figure out this, whether if it's a maxima, minima, or a saddle point without the graph, of course. Well, of course, I think just by looking at the graph, at the first graph, you can see if you have a switch from a positive to a negative slope, that would imply that you have a maxima. You have you're increasing and then decreasing the function. That would be a maxima. I'm going to write it up here, a maxima. And I think it's pretty evident. You see this is like the top of a hill, sort of. And you can pretty much say the same thing for the other guy. You are first decreasing, and then you stop, and then just go increasing, and that would imply this is a minima. What right here would be a minima. And just suppose you wouldn't have the graph. Okay, so I'm going to make this funny test. I'm going to suppose we didn't have this graph, so I'm just going to write this line just to locate, here. I'm going to say here, and why not here? Yeah, here. The x equal to -1 and the x equal to +1. I'm going to pick up values for the f prime of x, and I'm going to evaluate them. Suppose I'm going to evaluate here the f prime of, let's say, -2. If I evaluate the f prime equal to of -2, I will get here in return, I will substitute, let's say, the derivative, the -2, will be 3 times the -2 squared minus 3. I'm going to substitute it. I'm doing this, of course, because this procedure will help in the case you wouldn't have the graph. So that's why I'm doing it. Now, if you solve for this, would be here, we have positive 4 times 3, that's 12, minus 3, that will be positive 9. And the thing is, I just picked this value of -2 to prove that we got a positive result. A positive result would imply that this piece of, from negative infinite up to this x equal to -1, the function will be ascending. There it is. And that's why we got this positive area on the derivative graph. And if the thing is, feel free to try it on your own, but if you would have picked here, instead of a -2, a -5 or a -10 or a -1000, it wouldn't matter the number. But the thing is, you will always get a positive number as an output, and that would imply that we'll be ascending the function for all the values up to the -1. Now, I'm going to do the test with a value between the -1 and 1. Let's say I'm going to pick f prime of 0, which is typically the simplest one. F prime of 0 will be, of course, 3 times 0 minus 3. And, of course, we get a negative result. This negative result would imply that the function in between these two values would be descending, or would be negative, in this case for the slope. Descending, and that's why you got this period of the function where the values are going down, and you have this negative area in the derivative, the descending part. Descending, much nicer. Now, let's just finish the testing with the f prime. Let's say f prime of 2. Why not 2? So be 3 times 2 squared minus 3, and this would be, actually would be the same result as the previous. That would be 4 times 3 will be 12, minus 3 will be 9. We get at the end, what we get is a positive result, which if you look at the graph, you have this positive area, and after this minima, you see the function is growing up, again after the value for x equal to 1. So it will be the ascending. There it is. Well, the thing is, you can pretty much conclude just using this kind of method without having any graph, assuming you wouldn't have these guys, these beauties. Well, you could just look at it and say, well, if you have a function that is ascending and then descending, well, this clearly has to be a maxima. And if you, of course, have a function that is descending and then ascending up to a point, from 4 points, of course this guy, aquí se me fue una letra, es a maxima, should be a minima. Okay, and from this method, you can use it as it's called, well, pretty much the first derivative criteria. There is another criteria, but this is pretty good, pretty nice and easy, and it's very graphic, so I'm a big fan of it. You can pretty much reply this procedure if, in case you didn't have the graph, suppose you didn't have these beauties, that you could use something like this to prove or disprove whether a point is a maximum or minima. And then, well, let's get to another video to further explanation of this.